Hello, my name is Kwan, and this is my project, the active stabilization of a model rocket. I chose this project because I've always been interested in the aerospace industry and the engineering behind space exploration. And of course, model rocketry has been one of my hands-down favorite hobbies. Traditional model rockets are aerodynamically stabilized using fins. While this solution is generally lightweight and pretty reliable on a small scale, for full-sized launch vehicles, especially orbital ones, if you want to have fins on your rocket, this generally adds a lot of mass and unwanted drag, which are severe inefficiencies when you consider that in these applications, every kilogram of payload mass is extremely valuable. Orbital rockets then use a technology known as thrust vector control to maintain orientation. In this system, the engine is being constantly gimbaled by a closed-loop controller to counteract disturbance torques and ensure stability. Now, this approach is usually far more electronically and mechanically complex because it involves accurate sensors, precision mechanical actuators, and specialized guidance software. So it's generally not seen outside of orbital class launch vehicles, and certainly not on the model scale. This project then aims to demonstrate the feasibility of miniaturizing these crucial rocket subsystems by implementing an active stabilization system using TVC technology on the model scale. Now, some background. Fins maintain stability by generating a restoring torque whenever the rocket's orientation deviates from its velocity vector. So whenever the rocket strays from its course, the fins will gain an angle of attack to the wind. So essentially they cross the wind at an angle, much like the wings on a plane. And so consequently, this generates a lift force counteracting the direction of the perturbance. So essentially it creates a restoring force that wants to return this rocket to its original heading. Such a system is known as passive stabilization, since no input from the rocket is required to keep itself stable. Thrust vector control is a form of active stabilization. Electronic systems must constantly monitor the rocket's orientation using sensors like gyroscopes, or on more advanced rockets, accelerometers and perhaps GPS systems. And then it must deflect the thrust vector of the motor accordingly to implement the necessary course corrections, that is, physically changing the direction of the motor's thrust. The advantages of TVC systems include a reduction in overall mass for a larger rocket. Of course, for smaller rockets, fins are often sufficient. The ability to steer to a set orientation and increased performance in terms of accuracy and dependability. We must remember that fins, of course, depend on aerodynamic effects, and wind can have a great impact on the stability of your rocket. Now, moving on to our methodology. The control dynamics are one of the most major parts of it. This is essentially the algorithms that tell the rocket how to correct for a given deviation in its orientation, what output to send to the TVC gimbal, how to correct for that. At the heart of active stabilization is a feedback control loop. A diagram of that is shown below, the control logic of the rocket. On both the pitch and yaw axes, a gyroscope measured the orientation, which was inputted into a PID algorithm sending commands to the TVC gimbal. So in this diagram, we see here that the orientation is measured by our gyroscopic sensors. And this is used to calculate the error, essentially how much the rocket is deviating from the orientation we want it to be at, which is straight upwards. This is fed into the PID controller. This is the algorithm itself that determines what output should be sent to the engine to correct for that error. The PID controller has three parts: a proportional response, an integral response, and a derivative response. The proportional response generates the actual feedback response to the error. The integral response corrects for the steady state error, and the derivative response accounts for the rate of change of the outputs. All in all, it's a pretty well-rounded algorithm, but it does require extensive tuning. The PID's output is sent to the TVC gimbal, which then physically changes the rocket's orientation through the flight dynamics. So that's the actual physics, the rotational dynamics of the rocket and its flight. Of course, the orientation is measured again using gyroscopes, and the loop is closed. In order to tune the PID gains, these are the constants modifying each of the different responses in the PID controller, a flight simulation was coded to model the dynamics of flight as well as the PID response. A picture of one of these outputs from the simulation is shown above. We have the trajectory of the rocket itself, the X direction, its displacement here, and the Y direction, its displacement. That's the actual shape of its trajectory. This is the orientation plotted over time, the TVC output's direction plotted over time, and this is the response from the PID algorithm. To improve realism, the simulation modeled accurate motor behavior by interpolating imported data points from recorded rocket motor thrust curves, which are available online. The simulation also accounted for the actuation speed of the TVC gimbal, the frequency of the PID loop, time delays during the execution of the code, and initial misalignments in the TVC mount. Using the Ziegler-Nichols method, the PID gains were heuristically tuned. So essentially, in Ziegler-Nichols, the integral and derivative responses are initialized as 0, and the proportional response is increased until the system experiences steady-state oscillation, in which case there are some formulae out there to tell you what to set your integral and derivative gains to. So to the right, yeah, that's our sample output of the simulation. The control system then had to be validated by putting the rocket on a 2-axis gimbal, allowing for rotation on the pitch and yaw axes. So essentially, the rocket here is free to rotate about that gimbal. This simulates the rotational dynamics of flight, and the guidance software is responsible for trying to keep the rocket straight up as it would do in an actual flight. Moving on to the flight computer and guidance software, all of the above-mentioned algorithms were implemented as part of the guidance software, which itself was hosted on the flight computer. The computer also contained all of the necessary sensors, power supply circuitry, and data logging capabilities to guide the rocket. It was built around a custom-designed PCB. We have a picture of that here. This is the actual finalized flight computer, and that's a schematic that's laid out in Autodesk Eagle. The computer was centered around a TNC 3.5 microcontroller, which is this green board over here. A B&O 055 9-degree of freedom inertial measurement unit, this component here, provided acceleration and angular rates data, while a BMP 280 barometer, which is this chip over here, recorded the altitude. Data was logged to the TNC's onboard micro SD card here, as well as a discrete W25Q32FV flash memory chip to provide redundancy in case the SD card were to be dislodged. So the flash memory chip acts sort of like a black box in the event of a crash. Outputs for up to 3 servo motors were provided, and a host of GPIO pins allowed for communication with external peripherals using I2C, SPI, and UART protocols. So there's the possibility of adding more sensors should the need arise. The flight computer ran off a 7.4 volt 2-cell LiPo battery. Here is the actual control the software logic of the guidance software. In the launchpad idle mode, when the rocket's sitting on the pad, the sensors are running and the TVC gimbal is locked, so the engine can't deflect at all. Once the rocket is launched, the software detects that through an upwards acceleration, and it enters flight mode. In this case, the software, all of the guidance software is running. The data logging is increased to a rapid frequency, so we're logging all of that data to the SD card and the flash memory. Once an onboard timer elapses, so the rocket knows that the parachute is ejected, it stops, the guidance locks the TVC mount once again, and prepares for landing. Once the downward acceleration is detected to be 0, the rocket knows it is on the ground, and it stops the data logging as the flight is now completed. A quaternion filter was also used to process raw angular rates data from the gyroscopes into a mathematical representation of orientation without gimbal lock issues. Gimbal lock is something that Euler angles will suffer from, and this is usually pretty disastrous in such an application. Inertial cues from the IMU is from here. We used to detect the different stages of the flight. Now, moving on to the physical construction of the rocket. All of these custom parts were 3D printed from PLA plastic. This flexible duct here was printed from TPU thermopolymer, which is a flexible material. The airframe was made from 74.4 millimeter craft paper body tube, and parachute ejection was achieved by ducting the gases from the rocket motor's ejection charge, which bursts after a set burn delay. And then the gases would be ducted around the sensitive electronics in the flight computer using this ducting assembly. It would push this piston, which would shoot out. The parachute would be stored in this space here. It is pushed out by the piston, allowing the parachute to deploy and the rocket to land safely. The TVC gimbal is this component here. 2 SG90 servo motors were responsible for changing the direction of the engine's thrust, and the flexible duct allows the seal to be maintained even when the TVC gimbal is not at this orientation. And now our results. The rocket was launched twice, both times achieving excellent stability and safe recovery. But here is a display of all of our graphs. We collected the data for the X orientation. This is the X orientation plotted over time. This is the Y orientation plotted over time. This is the PID outputs on the respective axes. This is the acceleration over time, and that is the roll orientation. From the graph, we see that the maximum deviations in the orientation were around 5.8 degrees on the x-axis and around 10.4 degrees or slightly higher on the y-axis. But both of these peaks occurred at roughly the same time, around 0.57 seconds into the flight. This was likely due to the rocket correcting for initial misalignments in the TVC gimbal. Deviations were within 5 degrees for the remainder of the flight. Roll orientation, however, was not controlled. With a 2-axis gimbal system like this, it's often difficult to control. It's impossible to control the roll without an onboard reaction wheel or a similar RCS system. So in this case, roll orientation was uncontrolled. That's not a major detriment to the stability of the flight. However, the data we recorded for altitude was inaccurate due to miscalibration of the barometer. The barometer has to be calibrated to the local weather conditions, namely the barometric pressure on that day given the day's conditions. Failing to calibrate it meant that the altitude data was corrupted. The excellent performance of the active stabilization solution, however, testifies to the feasibility of implementing miniaturized rocket subsystems. Now, in terms of future work has been already done on a new generation of the rocket with a significantly reduced diameter, in this case 50 millimeters instead of 74 millimeters, and entirely revised components. A new, more compact TVC mount using digital servos will increase precision, and a completely reworked flight computer using SMD mounting technology will provide more functionalities such as onboard pyrotechnic channels, as well as a switching buck converter to provide better power supply circuitry. A new mechanical parachute ejection system will allow for computer-controlled parachute ejection, which improves the safety of the flight as it gives the rocket the option to abort a flight by deploying the parachute should it detect a flight anomaly. The construction of the new prototype is already complete, and the rocket is awaiting static fire testing. The next generation vehicle will further demonstrate miniaturization in all subsystems of the rocket. And that about does it for my project.
That is really an awesome presentation. Thank you, Kwan. And I feel like this is really like a huge amount of work. How long have you been working on this project?
Yeah, this was I'd say like around a 1-year process from the first formulation of the idea. There was a lot of research gone into the various things behind it, all of the control theory, the algorithms, and the software. So there were multiple prototypes. Every single component essentially failed in the first time. The parachute ejection went through like 5 different redesigns. I wanted to use a rubber band at first, but that didn't work out. I tried to use a spring. I tried to even use magnets to push the parachute out before eventually settling on the duck design. The flight computer went through 5 different iterations. My first one was just a tangled mess of wires, and then they eventually got more reliable and refined. So overall, it was a year of a bunch of tests, a bunch of failures, redesigns, and then of course the final flights.
Okay, I can see how exciting or like the excitement you have been putting into this project. So for the control theories, I know it's really hard. How did you manage to learn all of these like theories before like getting started with this project?
Yeah, so I bought a book called Control, right over here, Control System Design, and that helped a bit with the theory. It's really difficult to understand, but what helped a lot was prototyping some actual was testing it in smaller scale models. So experimenting with the actual code, programming some PID responses in Arduino, and testing those out. So yeah, sort of experimentation and prototypes helped me get a grasp on how this worked. It took a lot of tries, even the simulation, right? But they were helpful tools to understand.
Totally, yeah. And about this whole project, can you let us know, like, since you have included a lot of the terms, like the abbreviations, but probably our general audiences are not very familiar with all these terms. So basically, what is the real like novelty or your contribution to this project?
Well, most model rockets are stabilized using fins. So this is a completely new system, which essentially adds computer guidance to a model rocket. It allows the model rocket to control where it's going using an active so it's actively controlling its course. This is much more complex than a regular rocket, which just requires on the wind to stabilize it with its fins. In this case, it's a computer running specialized software to tell itself where to go, to monitor its orientation, to correct for it, using a gimbal motor. So yes, essentially, it's a computerized rocket that's able to guide itself.
Awesome work. Thank you so much.